right, it's already, the deadline has passed, okay? So I'm not going to accept any more quizzes. All right, guys. How come there are so few of you coming to my lectures? You don't like me or what? All right, guys, listen. Let me put this on. Right. Good afternoon. I mean, I would appreciate, if more of you could turn up, because, so last week we talked about maximum likelihood estimation, or MLE, and I did 9 examples, one short of my target. Yeah. And today I'm going to talk, all right, before I start today, okay, let me give you some properties. Properties of MLEs, right? All right, the first property, number 1, is that the limit, okay, before I say that, let me write, suppose theta hat is an MLE of theta, right? Okay, the first property is that the limit as n approaches infinity of the bias of theta hat is equal to 0. So that's property number 1, which is the same as saying that theta hat is the same as saying that theta hat is asymptotically unbiased for theta, right? Number 2, property number 2 is that the limit as n approaches infinity is equal to 0, right? Which is the same as saying that theta hat is consistent for theta, right? Number 3, right, is the following, that root of n right, root of n times theta hat minus theta approaches a normal variable as n approaches infinity, all right? That's number 3. And finally, number 4, if g is a one-to-one function, I'm sure you know what a one-to-one function is, right? Don't tell me you don't know. I mean, you have done analysis, real analysis, right? If g is a one-to-one function, then g of theta hat is an MLE of g of theta, right? So these are the four properties I would like you to know. All these four properties apply for the case of one parameter MLE. That is, theta is just a scalar, right? Right? Scalar meaning just one number, right? It's not a vector, okay? Now, before I go ahead, the next quizzes, that is quiz number 7, quiz number 8, quiz number 9, all of them will be on MLEs. So it will gives you enough practice. Right? 7, 8, 9 are all on one parameter MLEs. And quiz number 10 will be after the Easter break, right? So quiz 9 will be the last one before the Easter break. And when you come back after the Easter break, you will have the ARC coursework, which is due on the 29th of April, right? And then the week after that, you will have quiz 10, which will be the final quiz, right? Is that clear, guys? Yeah, all right. I just wanted to clear that up in case you have questions. And I got dozens of emails asking me whether there will be a test. I think I made this clear on the first day. There are no in-class tests for this course, right? Which should make you happy, I guess, or not. I mean, if you want a test, I can give you a test. Right? Okay. Okay. All right. Now, all right, in this week, I'm going to talk about two-parameter MLE. And I should make it clear that this material will not be examined. So this. All right, the two-parameter MLE is, I mean, I'm just talking about it because it will help you to learn. When you guys go to the second year, when you guys go to the second year, you'll be talking about two-parameter MLE. So I'm just talking about it now just to help you guys in advance, you know what I'm saying. When you go to the second year, you will know this material already, right? Okay. Okay, so now I'm going to talk about two cases, the continuous case and the discrete case. Right? Okay. So let's talk about the continuous case. Right? All right, suppose you have a random sample with PDF fx, and there are two parameters, theta 1 and theta 2, right? And we want to find the MLE of theta 1 and the MLE of theta 2. So the procedure is as follows. All right, step one. Step one, you write down the likelihood function. Right? This time it's a function of two arguments, theta 1 and theta 2. Right? So it will be the product it will be the product of the density function from 1 to n. Okay? Step 2 is to take the log of the likelihood function. Right? Remember, log of the product is the sum of the logs. Last week I gave you identities for the sums and the identities for the products. If you don't know this, some of you talked to me after the class and they said they did not see these. They said they had not seen these identities before. So if you hadn't seen those identities, make sure that you do remember them, right? Okay. They are very fundamental for, especially for this course and also for other courses you are taking. Okay. Step 3, because you have a function with two arguments, when you differentiate, you need to use partial derivatives. I'm sure. Do you guys know what a partial derivative is? All right. Don't tell me no. Okay. Okay. So you take the partial derivative of the log likelihood with respect to theta 1, right, and set that to 0. And you take the partial derivative with respect to theta 2 and set this to 0, right? Let me call this equation 1, equation 2, right? Right? So let theta 1 hat and theta 2 hat be the solutions of equations 1 and 2. Right? And step number 4 is the following. right? Did you see what I have written? So the step number 4 is this. If this, I know it looks kind of complicated, but this is the partial derivative, the second order partial derivative with respect to theta 1 hat. This is the second order partial derivative with respect to theta 2 hat. And this is the mixed partial derivative, right? Theta 1 hat and theta 2 hat, right? And this must be a positive number. If this is positive and this is negative, then the solutions theta 1 hat and theta 2 hat will be MLEs for theta 1 and theta 2 respectively. All right? Is that clear, guys? Yes. Go with me so far. I mean, if you have any question, just just feel free to pause me if you have questions. Right? Now, so that's the continuous case. So this is the continuous case. Now I'm going to talk about the discrete case, right? So suppose so here we are assuming we have a random sample with probability mass function Px with parameters theta 1 and theta 2, right? Yeah, so once again there is a 4-step procedure. The first step is to write down the likelihood function. Right, this is the likelihood. The likelihood is the product of the PMF over the n of data points. Second step is to take the log of the likelihood. Right? And the third step is to take the partial derivatives with respect to theta 1 and theta 2. So call this equation 1, call this equation 2. Yeah? Okay. Once again, let theta 1 hat and theta 2 hat be the solutions of equations 1 and 2. And step number 4 is as before. If So if this is positive and this is negative, right? Then right. All right. So this is the procedure is very similar to the continuous case. The only difference being that you have a PMF instead of a PDF. So that's the only difference. All right. Okay. Okay. All right, guys. Now, the next thing, I'm going to do some examples. As always, I don't know how many examples I can do, but I will start with a famous example. Can you be quiet, please? Right. Example 1 is, suppose now, as you know, the normal distribution has how many parameters? 2, right? Mu and sigma. So the procedures that I have just described should be applied to the normal distribution, right? Because the normal has 2 parameters, right? Okay? So let's see how it works. Step 1 is to write down the likelihood function for mu and sigma, right? So it's going to be the product going to be the product of the density function of the normal, right, which is this one. I'm sure all of you know. Yeah? Now if you do this, yeah, if you simplify this, this becomes this, right? Step number 2 is to take the log of the likelihood function, so the log of this one, which will be right. That's step 2. Okay, you with me? Now step 3. Step 3 is to take the partial derivatives with respect to the 2 parameters. So let's start with mu first. Okay. This is your calculus comes in. All right. Tell me, what's the partial derivative with respect to mu? I mean, you did the whole semester 1 doing calculus and vectors, or vectors and calculus, right? So what do you think the partial derivative will be? Yes? This is the partial derivative, right, with respect to mu, right? So this will be, to simplify this, you get this, right? And you can simplify this further. You will get this, right? And let me set this to 0, and let me call this equation 1, right? Okay? Right, now the next thing, let me take this a little bit up, like this. Hopefully you can still see this. The next thing is to take the partial derivative with respect to sigma. Now the partial derivative with respect to sigma is going to be minus n over sigma right. This is, can you see that? Yes. So this is the partial derivative with respect to sigma, right? And let me set this to 0 and call this equation 2. Now, let me ask you, what can you say from equation 1? What is the solution for mu from equation 1? From equation 1, you can see that the sum of xi is equal to n times mu. So this implies that mu hat is equal to 1 over n times the sum of xi, which is x bar. Yes? So the solution for equation 1 is the sample mean, x bar, right? Now move this up. From equation 2, I'm gonna substitute, in place of mu, I'm gonna put mu hat, right? From equation 2, you can see that sigma squared hat is equal to 1 over n yes, right, which is the same as 1 over n all right. Are you with me, or you lost already? You guys with me already? Yes? Yeah. Right, this is only step 3. Now we've got one more step to go. In order to make sure that this is an MLE, we need to show step 4, right? Okay? All right, let me take this away. Step 4. To do step 4, we need to compute the second order partial derivative, right? Which is going to be like this. I'm not going to bore you by asking you what the second order derivatives are. So I'll just write them down myself. Okay, so the this is the second order partial derivative with respect to mu, and this is the second order partial derivative with respect to sigma. Right? And the mixed derivative with respect to mu and sigma is this, right? I mean, you can check this yourself. I mean, all right, I'm not gonna. I'm sure all of you know how to differentiate better than me, right? So, okay, so now the next thing we need to do, is, I mean, these are partial derivatives, second order partial derivatives with respect to mu, sigma, and right. But what we need, in order to check condition 4, what we need are the second order partial derivatives right, and this will be this, right, and I mean, if you don't follow, if you don't follow this, don't be bothered, because this material will not be examinable for this course. Right? Now, this guy here we can simplify further, because it's equal to this. Now, sigma squared hat, if you remember just a few lines ago, we showed that sigma squared hat is equal to this, right? So hence, n times sigma hat squared will be n times sigma squared hat will be simply this, right? Do you see how I got from this line to this line? Right, using the fact that sigma hat squared a few lines backwards, you see it's equal to 1 over n times this, right? So what you have here is minus 2 is equal to this, right? So we have shown that the second order partial derivative with respect to sigma is equal to this. All right, and one more thing. All right, the mixed partial derivative, which is this one. Sorry, I don't know whether you can see this. No, now you can see it. This is the mixed partial derivative. So you should replace mu by mu hat. You should replace mu by mu hat and sigma by sigma hat. You will get this, right? Now this is we know that the mu hat, come on guys, we know that the mu hat is equal to x bar. Now can somebody tell me what this sum is equal to? I mean, if you've done all the 5 or 6 quizzes, you should know what the sum is equal to. Come on guys, are you tired or what? Huh? It's equal to what? It's equal to 0, right? Because remember, the sum of xi minus x bar from I from 1 to n is 0. You forgot to know what? Was part of quiz 1. Do you remember doing quiz 1 long time ago? You know, I think part of quiz 1 was to show that the sum of this is 0, right? Okay. So we have shown, just to summarize, what we have shown so far is the following. Let me do a box. We have shown that this guy is equal to this, right? And we have shown that it's equal to yeah, and we have also shown that the mixed derivative, the mixed partial derivative, is equal to 0. All right, are you guys with me or not? Yeah, and so what remains to show is to check the condition, right? So we just need to check the condition. Remember, the condition is the following. The condition is that this times this minus this must be positive. This multiplied by right? We must show that this is a positive number, right? So this is, using these, we have 2n over sigma power 6 times the sum of xi minus mu hat squared minus 0, right? Okay? Which is clearly positive, right? Because anything power 6 is positive. Anything power 2 is positive, right? So this condition is satisfied, okay? We must also show that the second order derivative of this is negative. But we know that this is equal to minus n over, which is clearly a negative number. So both conditions, remember these conditions. Sorry, not this one. I'm looking at the wrong one. Where am I? It's here. Remember these conditions. Oh. Man, what happened? Come on. Oh, here we are. You see? It's magic. Remember these conditions. Hello guys. Remember, these are the two conditions that we need to check, right? This is the first condition. Shh. This is the first condition and this is the second condition, right? And both conditions are satisfied, right? And hence, the conclusion is that right, hence So the conclusion, after a long process, I thought it might take the whole day. After a long process, we have shown that the mu hat, which is x bar, and sigma hat squared, which is this one, right, are the MLEs for mu and sigma, respectively, right? Are you guys okay with this or not? Yes? Any question? I mean, I'm teaching you this material just for your benefit. Although it's not going to be examined, when you go into second year, you know, you can be more confident. Yeah? You know what I'm saying? Okay. The next all right. The next one, this is example 2. Come on, guys. Are you ready to go home or what? Why are you packing up already? Yeah? 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 Example 2 is the following. All right, this is example number 2. So this distribution is known as the, if you don't know the name of this distribution, I will write it down. If I can find my pen. Yes, here we are. This distribution is known as the Laplace It's known as the Laplace distribution, right? And the first step is to write down the likelihood function. This is the product of the density function. So if you do that, you get step number 2. Okay. All right. And step number 3 to take the partial derivatives with respect to mu. So this is going to be call this equation 1, and partial derivative with respect to sigma, yeah, it's going to be minus n over sigma all right, call this equation 2. Now before you come on Thursday, I would like you to have a try and solve equation 1 and equation 2 for mu and sigma. Right? I mean, with all the calculus you've done, you should be able to do it. Right? Try to solve these two equations for mu and sigma. You guys okay? Yeah. Any questions? Let me know, guys. And I would like more people coming to my lectures. Maybe ask your friends to come to the lectures. Hello.
This is the same as this, right?
Yes, sir.
Also, this needs to be positive, negative. Inside. Because it's not as minimal in the 3D multivariable differential. If this is positive, it's not.
It can be anything. You're late, madam.
Condition for in here.
Yeah. It should be a power 2, yeah. Hello, sir, yeah. Where is the other guy? Yeah.
And other question, this means that this partial derivative is evaluated at theta 1 flat,
Yes,
right?
yes. Yeah. Hello. Yes, sir.
Here.
Yes. There should be a power. There should be a power 2. I missed it. Yeah.
That's all possible.
Yeah.
But here, I don't understand how do you choose which parameter is first?
No, you differentiate with respect to theta 1 twice, and then substitute theta 1 hat. Like what I did in the example.
But why not theta 2? Why theta 1 but not theta 2?
It's the same. It doesn't matter.
It doesn't?
It doesn't matter. It will be the same. Yeah, it will be the same. Yeah. How are you, man? Did you sort out your lab session?
Yeah, those are another one.
Did you finish the lab? You didn't finish? Oh, you can come and see me in my room if you want.
No, it's okay, I'm going to.
Hello.
So I found this book online to help supplement this course. And I was wondering how much of this stuff you will teach. And if there's anything that you won't teach. So that the book doesn't cover that you will teach. I have the contents page here.
No, it's basically what is in the. This is the only material that is not in the printed notes.
Okay.
Yeah, everything else is in the printed notes I gave you. Yeah.
Okay.
So this will. I think this is too much for you.
Okay.
I mean, it's this like multiple random variables and so on. This is more like probability 2. Which you take in next year, year 2, right? I don't think you will learn this in my course. No.
Okay.
Yeah. Maybe you will also learn part of this in statistical methods, which is again at year 2. Yeah. Okay. So for this course, I mean, you just need to know the stuff from the printed notes, but with supplementary, what I teach here is on top of what is on the printed notes.
Yeah. Okay.
It's more theoretical side of what is on the printed notes.
Okay then.
Yeah.
Okay.
Does that answer your
Yeah, I
question? or-
suppose. Yeah.
Yeah, thank you. Hello guys. You alright? See you later. See you.